Welcome everyone. In the previous video, we have studied the basic theory of E-plane resonance isolator and H-plane resonance isolator. Now in this video, we are going to present a numerical example how to design an E-plane resonance isolator. The problem is to design an E-plane resonance isolator in X-band waveguide. Actually, the waveguide that we are going to use it is WR90. Which has a dimension about 2.2 centimeters in A and 1.1 centimeter in B. And this WR90 waveguide is designed to operate from 8.4 to 12.4 gigahertz, which is used in X-band. So design an E-plane resonance isolator in X-band waveguide to operate at 10 gigahertz with minimum forward insertion loss and 30 dB reverse attenuation. So the main item which has been presented here is the reverse attenuation at this frequency is 30 dB. Use the thickness of the ferrite is 0.5 millimeters. So the value of T is 0.5 millimeter, and the saturation magnetization as 4 by ms equals 1700 Gauss, and the line width of this ferrite material delta H is 200 orested, and epsilon r, the permittivity of this ferrite material, has epsilon r equals 13. So if I'm asking you to design such E-plane resonance isolator, it means that what is the distance of the ferrite slab from the wall of the waveguide? What is the value of C? What is the length of this ferrite slab? What is the biasing magnetic field H naught? So these are the main points which should be determined from here. The given data is the thickness of the slab, the saturation magnetization of the slab, and the line width of the slab and the permittivity of the slab. After designing this E-plane resonance isolator, it is required to determine the bandwidth which the reverse attenuation is at least 27 dB. So effectively, we are going to design this isolator to be 30 dB at 10 gigahertz. When the frequency deviates from 10 gigahertz, the reverse attenuation will be less than 30 dB. So the allowed bandwidth is the reverse attenuation is at least 27 dB. So what is F1 and F2 and what is the difference between them, such that F1 has 27 dB and F2 has 27 dB. We are going starting from the constant, magnetic constant gamma, which is a global constant, which is 1.759 multiplied by 10 to the power 11. Omega naught, the precession frequency or Larmor frequency, it can be obtained as mu naught gamma H naught. H naught is the biasing DC magnetic field. And for the case of E-plane resonance isolator, the resonant frequency omega is obtained as the square root of omega naught multiplied by omega naught plus omega m. Omega m is the magnetization frequency, which is given by mu naught gamma multiplied by ms. We already have ms, so we can obtain omega m. And we are designing this E-plane resonance isolator to be resonant at 10 gigahertz. So the resonant frequency omega would be 2 pi multiplied by 10 gigahertz. From this, we can obtain the value of omega naught. We have already omega m. We can obtain omega naught. From omega naught, we can obtain the required biasing magnetic field H naught. So the required biasing magnetic field in this case, H naught, is 2820 oersted. This is how we have obtained the required biasing DC magnetic field in this case. Now, we have omega naught. We have the value of omega naught because H naught has been known now. We have omega naught and we have omega m. For a waveguide loaded with a ferrite slab, we have studied the propagation of this problem before, and we obtain the characteristic equation of this configuration in this form, such that we have here Kf, or the ferrite propagation constant K, or ferrite cutoff frequency, over mu extraordinary, and here we have kappa and mu. Here we have the air-filled waveguide cutoff wave number, which is already pi over A for the dominant mode. So Ka here corresponds to, Ka is the propagation constant. Ka is the propagation constant in air. Ka is the propagation constant in air. Ka squared equals K naught squared minus the longitudinal propagation along the waveguide. And here Kft, T is the thickness of the slab. Here Kac, C is the distance to the slab, multiplied by cotan Kad. D is the distance from A to the slab from the other side. This is the distance D. So effectively, the value of A, as I said, for WR90 is around 22 millimeters. The thickness of the slab is mentioned to be 0.5 millimeters. So from this, C is unknown. C is unknown now. We are going to look for the appropriate C. And the value of D is simply A minus C plus T. So the value of D is determined from the value of C. So this is actually the characteristic equation for the loaded waveguide with a ferrite slab, where Ka squared is K naught squared minus beta squared, and beta is the unknown propagation constant, and beta is actually a complex value, because actually we have complex propagation constant. It includes both phase constant and attenuation constant. Mu is defined from the mu tensor of the ferrite material as mu naught multiplied by 1 plus omega naught omega m over omega naught squared minus omega squared, where omega is the operating frequency here. The value of kappa is mu naught omega multiplied by omega m over omega naught squared minus omega squared. To include the attenuation or the losses, we are going to replace omega naught by omega naught plus j alpha omega, where alpha here is the attenuation in the ferrite medium, and this is determined from the line width of the ferrite. We know that the line width of the ferrite delta H is defined as 2 alpha omega over mu naught gamma. So we can replace alpha omega by delta H multiplied by mu naught gamma over 2, and already we have the line width delta H is 200 oersted. So from this we can obtain the value of alpha omega in terms of the line width. So we are going to replace omega naught, which we have obtained here, by complex omega naught to include the attenuation in the ferrite. And this complex omega naught will be replaced here in mu and kappa. And from mu and kappa, we can obtain the extraordinary permeability mu E as mu squared minus kappa squared over mu. The propagation constant in the ferrite is obtained as K ferrite squared equals omega squared mu extraordinary multiplied by epsilon. Epsilon is epsilon naught multiplied by epsilon r, and epsilon r is 12. So here is mu naught multiplied by mu e, or mu extraordinary in general, multiplied by epsilon minus beta squared. And beta once again is the propagation along the z direction. So effectively, we can change the value of C here from 0 even to A. And according to the value of C, we can obtain the value of D. So D depends on C. And we solve this equation for each C to find out the solution beta, or the eigenvalue beta. And the eigenvalue beta here, it will be complex quantity, real beta and imaginary beta. The imaginary is the attenuation coefficient. And because this is an equation of second order, we have two solutions. So we have beta plus and beta minus, and alpha plus and alpha minus. For all the problem, we are going to make the frequency fixed at the beginning to be 10 gigahertz. So K naught here is omega squared mu naught epsilon naught. So we are going to replace omega by 2 by f, and f here is 10 gigahertz. So the frequency is 10 gigahertz, is included in K naught here, and is included here also. Here it is a function of omega here. And effectively, alpha omega is included completely in the line width. So this equation now, the independent variable is C. We are going to change C and solve this equation for different values of C to obtain beta plus, beta minus, alpha plus, and alpha minus. So we can find for different values C over A from 0 to half, and we are solving the attenuation coefficient alpha plus and alpha minus. And it should be noted here that the attenuation coefficient for the propagation constant is in dB per meter, or in dB per centimeter in this configuration here. As I said, we have two solutions here for beta, and beta is complex, and the imaginary part of this beta corresponds to the attenuation coefficient. So we have alpha plus, the attenuation coefficient in the forward direction, and alpha minus, the attenuation coefficient in the reverse direction. According to this figure, we can note that the minimum attenuation in the forward direction would occur at the value of C over A at nearly 1.25. The minimum attenuation in the forward direction would occur at the value C over A at nearly 1.25. So according to this result, we are going to allocate the ferrite slab at the value C over A equals 1.25. At this point, the attenuation coefficient in the reverse direction, it is nearly slightly more than 12. It is nearly 12.5, nearly 12.5 dB per centimeters. So this is or 12.7, nearly 12.7 dB per centimeter. So this is the attenuation coefficient in the reverse direction for the propagation constant in the reverse direction. This is at the center frequency 10 gigahertz. The question now, if the value of C over A equals 0.125, what will be alpha plus and alpha minus for different frequencies? So we are going to return back to this equation to fix the value C over A to be 0.125, and we are going to change the value of omega, or the value of the frequency. So instead of fixing the frequency to be 10 gigahertz, we are going to vary the frequency. And for each frequency, we are going to calculate the complex beta plus and beta minus. And from the complex beta plus and beta minus, we are going to find alpha plus and alpha minus as the attenuation for the forward and the backward. So in this case, the forward attenuation coefficient alpha plus as a function of frequency, it would be this curve, while alpha minus, it would be this curve. So we can note that the attenuation in the reverse direction is maximum at the resonant frequency. Also in the forward direction is maximum at the resonant frequency, and it decays away from the resonant frequency in this way. Until now, we have designed the location of the ferrite slab and the biasing magnetic field of the biasing flap. Sorry. We have, until now, we have designed the position of the ferrite slab and the biasing DC magnetic field of the ferrite slab. The question now, what would be the required length for the ferrite slab? As we said, the attenuation coefficient here at the resonant frequency at 10 GHz is around 12.7 dB per centimeters, and it is required to find total attenuation in the reverse direction 30 dB. So the total length of the ferrite slab, it can be obtained as the required attenuation coefficient in the reverse direction over the attenuation coefficient in the reverse direction alpha minus. So 30 dB over 12.4, this is the exact value, 12.4 dB per centimeters. This means that the required length of this slab is 2.4 centimeters. So to obtain 30 dB attenuation, it is required to allocate the ferrite slab at C over A equal 1.25, and we have a length of this ferrite slab 2.4 centimeters, and this slab should be excited by a DC magnetic field equals 2820 oersted. Until now, we have designed this attenuator to be centered at the frequency 10 GHz. The question now, what is the bandwidth of this isolator such that the minimum attenuation in the reverse direction is 27 dB. So 27 dB, it means that if I have deviated the frequency here, the value of the attenuation coefficient, per centimeter will be less than the maximum value. So we are going to design for 27 dB over 2.4 centimeters, which is the obtained length. We find that the minimum attenuation coefficient alpha minus, it should be 11.3 dB per centimeters. So we are going to take 11.3 centimeters as a horizontal line, and we get the intersection here with the frequency. So we can find that the minimum frequency is around 9.9, for example, and here is around 10.1 nearly. So in this case, the bandwidth is around 0.2 gigahertz, and the center frequency is 10 gigahertz. This means that the bandwidth, according to these requirements, is less than 2% of the center frequency. This is an example how to design an E-plane resonance isolator. In the following video, we are going to discuss another type of isolators, and we will see how to design it. See you in the next video.